In this video, I'd like to talk about the properties of exponents, specifically when we're looking at rational or fractional exponents. And before we jump into any of the example problems, I first want to discuss the three main properties that we'll be focusing on. So let me just make a little bit of room here. And the first property we'll look at is when you have two exponential expressions that have the same base and are multiplied together. So the base is the same in these, and we have multiplication. And when this is the case, you are going to add the exponents. And you can think about it that we're multiplying x here for this first expression, a times. So that is a times. And then we're going to multiply that, let me just make even more room here, by x to the b. So that's x multiplied b times. And so when we multiply these two expressions together, we have a number of x's here and b number of x's here. And so in total, we have x multiplied by itself, a plus b times. Now, it does often help to look at some different concrete examples. So for this one, we can look at a specific example. Let's say we have 3 squared times by 3 to the third. So this first expression is really just 3 times 3, and the second expression is 3 multiplied 3 times. And you can see that there are 1, 2, 3, 4, 5 of these. So this is really 3 multiplied by itself 5 times, but we could have gotten it from the rule here. This is 3 to the 2 plus 3 power. So this is one of the rules. One other rule that we want to focus on, let me scroll down a bit here, is when we have a quotient. So let's say we have x to the a divided by x to the b, and there are a couple different ways to look at this. For instance, you could think of this as x to the a times 1 over x to the b, where in the second expression we're dividing by x b times. And repeated division, remember, we can just rewrite with a negative exponent and then apply the rule that we just saw above. This is x to the a plus negative b, or just x to the a minus b. So when you have a quotient here with two exponential expressions with the same base, where x is our base, then we're going to subtract the exponents. We're going to take the top one and subtract the bottom one. And the other way that you could think about it, similar to how we looked at the first exponent rule, is that we have a x's up top. So that's x multiplied by itself a times. And we're going to divide that by x multiplied by itself b times. And we'll be able to make some cancellations. So we'll have it cancel out enough so that we just have their difference left over. And again, this would simplify to this subtraction here of the exponents. And let's look at a concrete example. Let's say we have 4 to the 5th power divided by 4 to the 2nd power. And the rule tells us we should subtract, so this should be 4 to the 5 minus 2, or 4 to the 3rd. But if we look at it from basic principles, we have 4 multiplied by itself 5 times in the numerator. And in the denominator, there are 2 4s multiplied together. And you can see that 2 of them from the top and the bottom are going to cancel out, since 4 divided by 4 is just 1. And so in the end, either by using the rule or by understanding it with basic principles, we end up with 4 to the 3rd. Now, the last exponent property we want to focus on is when we have an exponent raised to an exponent. So let's say we have x to the a, and we're going to raise that to the b power. So again, you could think about this with basic principles, but the rule in this case, when you have an exponent to an exponent, you're going to multiply. So this will be x to the a times b. But again, let's simplify this with basic principles. So in the parentheses, we're multiplying x a times, and we're going to raise that to the b power, which means we're going to take this expression and multiply it b number of times. So it'd be that x multiplied a times, and you can imagine doing it quite a bit. So this is a times, and let me just extend this. And so this goes on and on and on. And again, each of these is just x multiplied a times. So for instance, if there were 4 x's here and b was, let's say, 3, you'd have 4 of these times 4 more times 4 more. And so that would be 12 total, or 4 times 3. So this is another way to think about it. And again, we multiplied this x to the a, or x multiplied by itself a times, b number of times. But let's look at a specific example. So let's say we have 2 squared, and we're going to raise that to the 3rd power. And we know by the rule that an exponent to an exponent, we just multiply. 3 times 2 is 6. But with basic principles, we can understand this a little bit better. 2 squared is really just 2 times 2, and we're going to raise that to the 3rd power. So now we're taking this expression and multiplying it 3 times. So 2 times 2 times 2 times 2, and again 2 times 2 at the end, and you can count them. There are 6 2's here multiplied together. So these rules do make sense, and for this video, we're going to look at when these are fractions. Now, the rules, these properties do still apply for fractional exponents, or really any real number, but the proofs for those are a little bit complicated. So we're not going to focus on proving those statements, but it is true that a and b here and all of these examples can be any real number or any rational number for these specific problems. So with all of this in mind, let's actually look through some of the problems now.